And the inverse Fourier transform.
So, there's one last thing I'm going to do here. It's a little bit tricky, but the idea is quite simple.
Discrete Fourier transform.
I'm going to talk to
almost
the notes
identical.
Here, that's all right. So,
I should do it
the Jacobian matrix, we worked out this point here is a sink.
So we go
This
back.
is the saddle.
So this, the combined together, you end
We're
up
interested in the
started
solution that comes
the
out
sum
of the sink
from
and goes into
M
the,
equals naught
and out of the saddle and goes into the
minus
sink. This heteroclinic connection.
C
That is the
M
tripping wave solution.
hat
Now,
e to the power, and it's the same 2
the
pi
eigenvalue of this
I
is
M
given here.
over n.
So they're always negative,
Just
but
a
they can
positive
become
instead of a
complex.
negative. Yeah,
If
complex.
the,
It's just like this
square
Fourier transform, and it has this 1 divided by n.
is
So it's scaled how to get the expression for k, how to get the expressions for k and where they come from.
less than 2, sorry.
So
V squared
implementing this thing here naively, you end up with
going to
doing
spiral.
it's just a
And
matrix
then it
multiplication. So it's
whatever
an
happens is it
squared
comes in here, it has to
operations to
spin
go.
around, it has to go around an infinite number
It can be
of times.
massively sped up.
Okay, so there's no. Now, what does that
Discrete
mean?
Fourier
It means that
transform
beta's got to
in
become,
order
it
n
goes
squared,
around
and
zero,
the fast
swings
Fourier
from being
transform
positive to being negative.
is
We
order
can't have
n
beta becoming
log.
negative because that would mean we'd have a negative amount of our chemical.
So that's
that
an
means that
enormous
the
speed
velocity
up
has
because
to
of
be at
course
least
you've got at the end of
travelling rate has to
1,000.
be at least 2.
So this
If
is
we want to try and prove,
this is equal to
there's no
1,000.
reason why the saddle
10
can't
to
come
the
around
3
and go in
squared.
like that.
And this is equal to
Basically, we've got to
10
prove
to the
just
3
because
times the
the
log
log
of 10
spirals,
to the
it
3, which is
definitely beta has to become
approximately
negative.
3.
But
So every exponent.
If it
So
doesn't,
increasing the factor
just
points
because
by
it's
10
in the
here
spiral, we've got to
barely
prove
makes
that beta
any
never
change
becomes
and just
negative.
increases the
So
this
that's
one
what
increases the
argument here is
and
about.
make it go 100 times slower. This is going to make
I'll
it
try
only
and
go
explain
10
that
times
to us
slower.
here.
That was an increase high.
So what we've got, if we look at it, is we've got
Alright.
these two
So
equilibrium
one of the things
points
about the
here and
fast Fourier
here.
transform is that
And
it's
this is
only
the-
quicker
this is
if
the
the
gamma
number
axis.
of points is a power of
This is
2
the beta
or
axis.
something that you can factorize. So get the more you can, the more prime factors it has, the better. And if it's a
We've
power
got
of 2, it's optimal. And if it's a
gamma
prime number, if n is a prime number, then the
okay, which is
system
our
doesn't
terminal
work at all.
variable, is equal
Okay,
to
because what we're doing is we're going round, we've got a sequence of points on the circle that we're computing,
minus
right? And so the first time we go round,
Vy
we take every point. The second
The
time we
gamma.
square it, so we take every second point.
plus beta
And then we
times
start, we
beta
sort of
minus
coming
1.
back on ourselves,
We've got
essentially.
d,
is
I
the
don't know why I
idea.
keep writing it like that, but it doesn't matter. d beta dy is equal to gamma.
Let's just do it in
All right.
maths. Okay? So, we can, with 1, 2, 3, 5,
So what we do,
n minus 1, cn. Doesn't seem like we've got anywhere here, does it?
what we do is we set up this region here.
And then we can look at each of these in turn. So,
Down like that.
this is just another Fourier
And what
transform
we're
on
going to try and
half
do
the
is we're going to try and show that the solution
That's
to
the
this
sum
equation has to
equals
flow
naught
in
to
here, and
n
in
over
here.
2 minus 1.
So that means that once the solution gets
So you have
inside
2k
this wedge, it has to flow into this point.
e to
It
the
can't ever
minus
get back out here and
2
come round to do something terrible like that.
I
Okay, so we've got to look at
k
make sure that the flow's into this wedge.
times m over
So
n over 2.
get rid of these arrows I've drawn because we'll just talk about
So it's a
them.
half, it's a Fourier transform.
Okay,
on
so
half
this is the
length.
line here.
And this is more or less the
where,
same.
Gamma is equal
You've got to
to
pull a
minus
factor
k,
out, which is just a constant factor, 2 pi I m n.
Okay, that's the equation of that line.
But, you know,
All right,
2
so let's just have a look here at these different regions. So
This is the sum
the first two are really
from
easy.
k
Up here,
equals
we've got that
there at,
the
you know,
gamma
2 minus
dy
1
is equal to
C
gamma
of
0
2k
here.
plus 1,
So
so it's
the
every
gamma dy
second
is
point
beta
here.
times
It's
beta
still just
minus
another
1. This is
Fourier
always
transform.
positive. So on here, the gamma dy, it doesn't matter if it's going backwards or forwards, we just want it to flow
All
down.
right,
This is
so we
equal
can
to
basically write this. So this is a
beta
Fourier
times
these are just
beta
two Fourier transforms of half the length. So if you think
just
about it
always
like
greater than
this,
0. So the flow is always in here. So no problems. It can't
so
get back
let's
out.
assume n is
And then
equal
on this
to
line here,
1000.
we have d beta
1000, right?
dy is
N
equal to
equal to
gamma, which is
So
negative.
this thing here, we're going to have to do one. We're going to do this one Fourier transform here.
Whoops.
So that's going to take us
Gamma.
the n, n squared,
That's
right?
what the flow is.
N squared is
So the
10 to
region
the
here.
6 steps.
So that just leaves us
Now if
this
we go down
line
here,
where gamma is
we're gonna
minus
do
k
it
beta.
half
So
the
what we
length.
want, this is a bit
So
tricky.
it's if n is equal to not 1,000,
Grab
but
another colour
if
here
n is
and
equal
try
to
and like this, maybe.
1,024,
Okay,
we can just
so
keep
the
it halving
on the
forever.
slope of this line is
Okay, so that's the idea. It's
divided by
not
beta.
rocket science or genius. I mean, implementing it efficiently and things might be clever, but there's
Say
nothing very
here,
sophisticated
maybe
about
this
the
is a
idea.
little
You
bit,
can
you
sort
know,
of see what's
slightly
happening as you
careful
go
here.
around the
The
circle.
slope,
On every
K,
even one, you only land on the
slope.
even numbers, so you only need every second number.
Maybe I shouldn't write in this danger zone here.
And every odd one, you kind of do the
So-
same thing.
The slope of this line, let's just, is equal to k minus k, which is equal to gamma over beta. Now, let's imagine this flow up here, this line here, this is a solution, a flowing solution here. Then the slope of that is the change in gamma over the change in beta. So this is the solution. So the slope is d gamma d beta. Right? So, because it goes along here, d beta dy, and it goes up, d gamma dy. So if you divide them out, you're going to get this triangle, that's the slope. Okay, the dy's cancel if you like. Okay? So what we want, get rid of that, it doesn't help out. We want to have this slope here to be bigger, more negative, I suppose is the way to put it, than the slope here. So we want the gamma dy, the difference in slope. So maybe it's better to write it like this. We want d gamma d beta to be less than d gamma divided by beta. Okay, so that's our condition. If that's the case, then all the flows here are steeper and it's going to come into this region. We've got this parameter k that we're free to fiddle with to make it steeper. So this is the condition we've got to analyse. So then we've got to do a little bit of analysis on it. So I'm going to try and just write that up here maybe in another colour. So d gamma d beta minus gamma over beta is equal to, and then we've got this formula for it. So d gamma d beta is that divided by gamma. So it's minus v plus beta times beta minus 1 over gamma minus gamma divided by beta. And of course, gamma is k minus k times beta. We haven't used that yet. So this is going to be minus v plus beta minus 1 over k minus k. Got a few sign errors here, haven't I? Because there's a minus here, so that's going to become a plus. And this thing here is also going to become a minus, isn't it? Because this is minus here. Alright, and then we can write that, right, we can take out the 1 over k. So we're going to get k squared plus minus bk plus minus beta plus 1. So let's just go back to what we've actually done and maybe re-explain it. We tried to work it, we want the slope of this thing to be always flowing in. So we need the slope of the flow, this thing, to be net below the slope of the line, more negative than the slope of the line. So we work out the difference between them. So we want this thing here, this difference here, to be less than, we need this to be negative, less than 0. So we need k squared minus vk plus 1 minus beta to be less than 0. Now we know beta is always positive, so we need just k squared minus v squared plus 1 to be less than 0. And beta goes from 0 down here, from 1 down here to 0. So we've got to have k squared minus b squared plus 1 to be less than 0. So when is that going to happen? What value of k makes that true? What value of v would make that always true? So there's lots of ways of thinking about this problem, but this is we can choose k. We have liberty to choose k. So basically, you sort of feel like you should be able to choose some k where this is going to be some value of which this is negative, but it depends on v. So we can only find a k. Find a k if v is greater than 2. So, and for example, v is equal to 8 or something like that, then we can choose k is equal to 1, right? 1 squared minus 8. Or if k is equal to 2, we can choose 1 minus 2 plus 1. Okay, so what we already know that v has to be greater than or equal to 2 to get a travelling wave solution. What is interesting and what doesn't come out of this analysis, so we've proven the shape of the travelling wave solution, and we've actually proven that there's lots of them for lots of different values of v. And we've proven that v is equal to 2, the solution does exist, but it can't be any bigger than that. So if we finally go back to my notes, what we haven't done is shown that the solution, we've shown that there's actually lots of travelling wave solutions. The v has to be at least 2. But if you look at the speed of the solution here, maybe the t is 15, it's gone about 30. Its speed is equal to 2, and we haven't shown why that speed is equal to 2. We have not shown that. We've shown that it's safe to say that it's the minimum speed that we can get. So the wave moves at that minimum speed. There's the shape of that wave, exactly that shape. It's not quite obvious, but within this travelling wave coordinate.